Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Homological algebra is in many ways the study of complexes. And in this video, I want to talk to you about how complexes actually form a category. And in fact, by studying this category, we are able to study not only complexes themselves, but also how they relate to module theory. Okay, so the notation for the category of chain complexes over a ring R is often denoted like this, or with this more expanded notation, because in general you can replace this R with more general categories. And being a category, if you haven't seen this concept before, you can look in my playlist on category theory. But the main thing is it's an environment where you can talk about objects and also morphisms between them. Okay, so for example, we can talk about the category of R modules. Okay, so the objects are themselves just R modules, and you can talk about R module homomorphisms or R linear maps. Okay, so in this case, the objects will just be chain complexes of R modules. So they're things like this. Okay, often we'll denote it by C dot. So here's a C dot. It's a sequence of R modules and maps between them, such that the composite of any two consecutive maps is 0. Okay, and the thing that's new to this video now is I also want to talk to you about morphisms between complexes. Suppose you have two chain complexes, not only this C dot here, but also this C prime dot here. Okay, so let me just put in some missing notation here. So this is a C0 prime there. Okay, so here's our two complexes, C dot, the top one, and C prime dot, which is the bottom one here. Okay, so what's a morphism between these two? Okay, well, basically it's a commutative diagram of the following form. What we'll do is we're going to put in vertical maps, okay, between the corresponding terms. So from C0 to Z0 prime, C1 to C1 prime, C2 to C2 prime, and all the way back to wherever it goes. And similarly for any negative degree terms as well. And we want this to be a commutative diagram. So what does it mean to be a commutative diagram? So basically it means that all these squares commute. So if you start, for example, at any position along the top, say for example here, and if you go around this way, that map is the same as going around the bottom way. In other words, if you go in the ith slot, and you apply a di, so for example here, this will be d1, and then f0, so di, and then fi minus 1. That's the same as if you just apply this vertical map fi first, and then you use the differential down on the prime complex C prime. Okay, so that's a di prime. So if this equation holds for all I, so in other words, all these squares commute, okay, then this is called a morphism of chain complexes, or simply just a chain map. So the next thing that we need to have the data for category is not just morphisms, but how do you compose morphisms? Okay, so suppose now you have not just this morphism here, but we have another morphism from C prime to a third chain complex, C double prime. Okay, so what do we need to do here? So let me just perhaps write a little bit of one out. So suppose now you have a C1 double prime here, C0 double prime here. And perhaps you've got this prime morphism, so you've got something like this here now. And now what you want to do is you want a composite, so you want to map from this chain complex down to this double prime complex here. And I hope you can see how you can put in vertical maps from the top to the bottom. You just compose these two. Okay, so that's what you're going to do. So in degree I, okay, what is the composite? F dot with F prime dot. Okay, so what you do is just take the ith components, okay, of the chain maps, okay, and you compose them, and that'll go from Ci to Ci double prime. So basically, in degree 1, it will be just the composite of these two. Degree 0 is the composite of these two, and so forth. Now, of course, what you'll need to do is you'll need to check that the condition of commutativity of squares still holds. So let's just do this fairly quickly, and then we'll see that this does define a composite, which is actually a morphism of chain complexes. Okay, so we need to show that it doesn't matter whether you go around this way or around this way, we get the same thing. So the composite now of these three maps is a composite of these three maps. Okay, now if you go around this way, right, the composite of these two is the same as going down around this way. So this way here is the same as this zigzag combination of these three morphisms. But these two are the same as these two since this square commutes. So that means that this is the same as this here. So that tells you that this whole rectangle commutes because essentially you've used the fact that these two squares commute to show that this rectangle commutes, and hence what I've defined here is indeed a morphism of chain complexes. Of course, that's just the data for a category, and the thing that you'll need to do is to check the axioms. So let's just briefly have a look at it. I guess the first thing is you'll need the composition to be associative, but essentially this follows by term-wise associativity of composition of functions. Okay, so the other thing that you'll need to know is, well, there should be a distinguished identity morphism. So if C prime equals C dot, what is the identity? So these two are actually the same. Okay, of course you can put just identity maps in each and every slot, and it's not hard to see that as a result, if this is the identity, for example, if all these Fi's are identities, okay, that means that the ith degree morphism, okay, of the composite with this identity is indeed the same as the original. Okay, so that is the identity in this case. So there we have it. We have a category. Okay, so this is a very, very good way to study complexes, is by looking at the category of all of them. And in fact, it's a category that's very, very much like the category of modules. So what are some things that the category of modules has, which are nice features which allow you to study it? Okay, so the first thing is that you can talk about notions such as the direct sum of modules. And in fact, you can do the same thing with categories of or rather with chain complexes of modules. Okay, you can talk about direct sums, you can talk about kernels of morphisms, chain complexes, you can talk about images, you can talk about cokernels, you can ask as a result, okay, when is a morphism injective, when is it surjective? Okay, so for example, if you want it to be surjective, that means that the image is the codomain. Okay. So that's what surjective means. Injective means the kernel is 0, for example. Okay, and then you can similarly talk about short exact sequences. And to see why this is true, the proofs for all of these are more or less the same. Essentially, they follow from the fact that the category of modules have these properties, and we can just carry out these constructions term by term inside the sequence. And to do this, I'll just give a brief example, and that's the example of looking at the cokernel of a chain map, f dot from C dot to C prime dot. Okay, so let me just show you how that works. And it's quite easy. Okay, so suppose now we'll write it out more in full. Okay, so we have our morphism, chain map, morphism of chain complex from C dot C prime dot, that's given by f dot. So C dot I've written out here like that. C prime dot I've written out here like that. And remember, the morphism is just in each degree. There's going to be a morphism between the corresponding modules, and you want to make sure that these diagrams commute. Okay. So what did I say here is that we have to look term-wise at all the cokernels. So here's a morphism in the category of R module, so we can look at its cokernel of F2, and just to remind you what that means, it just means you take this codomain C2 prime and you mod out by the image of this map here. So that's the cokernel. So it's going to be a quotient of this, so you have a map from C2 prime to this cokernel. And you can do this in each slot. Now, you do this in each slot, but then the question becomes, well, this isn't a complex now. It's just a sequence of modules. There's no maps between them. So what you want to do is you want to show how there are induced maps between them. So how do you go from here to here, for example? So let's just pick some element inside this cokernel. It's going to be a residue class of something inside C2 prime. So it's some residue class. So you can to get over here, of course, we want to use the maps here. We can look at something which maps to it. Let's call it C prime, which maps to it. And then to map it over here, what we can do is we just send it over to here and then send it down to here. Okay? And that gives you a map from here to here, but it depends on this choice of the lift. So the thing that you have to show is that it's independent of the choice. How can you change it? Well, you can change it by something in the image of F2. So let's pick something in the image of F2. So if it's in the image of F2, it comes from something inside here. And you're going to vary it by that. So if we add in something like this, we want to make sure that it doesn't change. So that's changing the C prime by the image of something in here. It doesn't change what happens when you go over here. Okay, so let's see what it changes by. So you have the image of C in here, and you map over here. So if you go down this way though, and then go down this way, well, going across like this, since this diagram, this square commutes, it's the same as if you go around this way. And then you go around this way and then go down. But remember, this is the cokernel, so that means the composite of these two is 0. Remember, this is just quotienting out by the image of this. So where this C lands in over here, whether you go this way or this way, it lands inside the image of this F1, so it goes to 0 here. So changing the C prime by another element in its equivalence class, okay, so another element in this coset, okay, change, but it means that, well, you basically pick some C, which maps like that, and you change it by the image of C all the way down here, which, as we've seen, is just 0. And hence this is a well-defined map. And since it's a well-defined map, okay, that gives us this map here. And you can check that by the way it's defined. Since we went up and went across, okay, we can come back down and go across. It's the same thing. So this squared commutes. And similarly, you can fill in to get the rest of this complex. Okay. And moreover, not only do you have a complex here, you have a morphism from this C prime dot to this cokernel of F dot. Okay. So that is a morphism. And clearly it's surjective in the sense that each and every single one of these is surjective. Okay, so that gives you the notion of cokernels. Great, so that means that we have a lot of notions that we can talk about when we're looking at chain complexes of modules. So the next thing I want to do is to see how do we relate the study of complexes back to module theory? Well, the most important function here is homology. And so we talked about homologies, the homology of a complex, but now since we have a category, we can see, well, what about the homology of a morphism of complexes? And the key point here is that this homology is actually a functor. So I want to talk about the functoriality of HI. And so what's the proposition here? So given a morphism F dot from C dot to C prime dot, that's going to induce a morphism on the corresponding homology. So we can take the homology of C dot HI C dot, okay, and also the homology of C prime dot HI C prime dot, and we have a morphism of these R modules HI F dot, and it's defined as follows. So remember what this is. This is defined to be the cycles modulo the boundaries. So it's a coset of the boundaries, BIC dot. And what we do is, well, this is living in degree I. This set is living in degree I. It's an I cycle. So we can apply Fi to it to get you Fi of Z. Okay, and we look at this, what I claim is an element of here. So there is a well-defined map. And I guess the other thing that's important is, and HI is functorial. Okay, so this is a very, very important way that you can connect the theory of complexes back to module theory. Okay, so let's just see some of the reasons why this is true. Okay, so the first and most important thing is to check why this is a well-defined map. Okay, and let's just remind ourselves what's going on here. Okay, so firstly, what is the homology of this complex C dot? So here's the complex C dot I've written here. Okay, so the homology in degree I, so that's going to be a subquotient of Ci. So firstly, we look at all the cycles inside Ci. Okay, so what's that? So that's an element Z inside here. So if you apply the differential, it goes to 0. Okay. So you look at all these elements and you look at all the cosets with respect to the BIC dot, which is just the image of this. We'll have a look more at that later. So what I want to do is I want to map this down to Fi of Z. So that's what I do here. So this goes down to Fi of Z, which you have here. And the thing is that if you want to map to the homology, then this better be a cycle in the C prime complex. So it has to go towards 0 here. So let's see where it goes to. Well, going around this way is the same as going around this way. This is already 0. So this, when it goes down, is going to go to 0. So that tells you that this is indeed a cycle. So at least that's fine. So this at least lives in the correct, this expression here lives in the correct codomain. Okay, so that's the first part of showing that it's well-defined. What's the second part of showing that it's well-defined? Well, here you need to pick a representative of this coset. So what happens if you picked a different one? Will you get a different homology class here? And of course you want to show that you don't. So let's change this by a boundary. So suppose here you want to add to that this B, which is a boundary inside here. And you want to show that when you do this, when you map it down here, okay, you're going to get the same homology class. Okay, so remember this is where this element goes to. This homology class is just the homology class of you apply Fi to it, to this element. So we're going to apply Fi to that element. This is a boundary, so I guess it comes from something inside here. That's what it means to be a boundary. It's the boundary, this subgroup here, or this submodule here, is just the image of this differential here. So this C maps to this here. Now, what's the difference when you map to here? Do I get something that's still in the same homology class? Okay, so are they in the same coset? Well, to work out how this goes down here, of course, we can use the commutativity of this square and map it down here instead. And that gives you some C prime. So where this maps to is where C prime maps to. But where C prime maps to is clearly a boundary here. So you're just changing, if you change this Z to Z plus this B, what you'll do is you alter this Fi of Z by basically the image of this element, okay? And that is clearly in this boundary here, so it's the same coset, so it's well defined. And that shows you that the homology map here is well defined. And the only thing that you now need to do is to show that it's functorial. So the first thing that you need to do to show that it's functorial is that it takes identity to identity. So if these two are the same, and all these maps are the identity maps, of course, then this is the identity map. So of course there's no change here, so this is indeed the identity. And then the second thing is that, well, if you have a composite of chain maps, so if you have a chain map like this, what's it doing to the homology? Okay, so in this case, you can kind of see what's it doing. Okay, so really what you do is you just apply the corresponding functions on representative elements. So of course, if you have a composite, okay, either you apply the composite, or if you want to do the composite of homologies, you apply them each in turn and you get the same result. And that allows you to relate the theory of complexes back to modules by using the functoriality of the homology functor. I hope you enjoyed this adventure in pure mathematics.